to help you build that intuition for convolutions. So let's say I have a figure of this good-looking gentleman, Professor Hinton, as my x. This is x. And I have my w, with which I am going to convolve the image. And I get the version on the right. So this is x convolved with w. What is this convolution doing? And why? What do we think?
This seems to be just scaling the image.
Scaling the image, okay. Shima?
It actually impacts on the center pixel of each region which lies on, and then is average over all local pixels, and somehow it blurs the image because the center pixel will be multiplied by 4, and yeah, the center image is multiplied by 4, but the others are, and the border pixels are go out of the computation, and yeah, somehow it's
I think I mean that's absolutely correct. So, and the keyword there was blurring. So although the original image also doesn't seem to be of high resolution, certainly the one on the right-hand side is the blurred version of that. And Shima said it correctly in that the way that this kernel works is that for every position that we put our kernel on top of the image, we're going to take the element-wise product and then sum over those values. And then we're going to spit something out to be just, so here it's going to be just one pixel here is going to correspond to the patch of image convolved with that kernel. And what does the kernel do? The kernel is going to take the center value of that pixel at that same coordinate. It's going to multiply it by 4, but then it's also going to sum it up with all the 4 directions adjacent to that center pixel. So in a sense, it's averaging the values of every pixel with its immediate 4 neighbors. And so the effect of that is that it's going to blur the image. Okay? What about this one? What is it doing? At least visually, what is this kernel doing to the image? Yes, Jim.
It sharpens the image because of...
Right. At least everyone can agree that the image on the right-hand side is a bit more sharp. And you can follow a similar line of argument again and say, okay, at every point that the kernel lies, there's going to be an inner product that's going to give us 1 pixel there. And what it's doing is taking the center pixel, multiplying it by a large number, in this case 8, and then subtracting the effect of everything around it. And that gives us sharpening, right? Sharpening just means that there is a sharp contrast between every pixel and its surroundings. Okay, now you might be wondering, what if this number is 4? So let's look at that. Yes, this is sharpening. What happens here? What is the image on the right, Hamza? Edge detection. Right, so now we've multiplied every center pixel by 4, and then of the same magnitude, we've subtracted everything around it. And now we get something known as edge detections. Why do we get this funky pattern, and why do we call it edge detection? Because edges are, literally in its name, the point which we have in the original data, pixel and neighboring pixels. So if any of the direction, like 4 direction pixel, is substantially different from the center pixel, then we're going to see, a high value in the output of the convolution. So this is known as edge detection. You can see where this is going. What about this one? Now this is known as a funky edge detection, or otherwise known as left to left to right edge detection. And left to right means that anytime if I'm going left to right, if I start off on a pixel that is black, and I move towards a pixel that becomes white, based on the computations you see in the kernel, then you're going to see a white value there. And anytime you go from the forehead, which is white, to an area which is black, like the hair, then you're going to see a black area. So what is right to left edge detection? Does the flip of that. Now, you might think that this exercise is a moot exercise, but there's actually 2 points here. The first one is that the convolutional, the convolution kernel on an image gives us really interesting properties with such a simple 9-weight combination and kernel operation. Right? We can detect edges, left to right, top to down, sharpen images, blur something, denoise, etc. with really just all these nine features. Most of the time, a lot of them were 0 anyway, so it was straightforward to deal with. That's point number 1. Point number 2, and this relates to our previous lecture about feature engineering versus feature learning. I want to kind of foreshadow what you'll see in the next lecture, is that these are hand-designed kernels that do very specific things for us on these images: sharpening, blurring, edge detection, etc. Now imagine that there was an approach that instead of there being, you know, a very solid like 1, 4, -1, whatever, very clean numbers, that you have an approach that can learn the values in these kernels. And then it can repeat that over multiple kernels and multiple layers, and then have very interesting properties arise. Oh, now we're getting somewhere. Right? You might be wondering, well, how does edge detection help me to do object recognition? That's just one step in the process. So if you can think about how these build on one another, then it's much more easy to appreciate that, oh, so CNNs built of successive layers of kernels doing various forms of transformations on my data might then enable me to perform object recognition with all its diversity and everything that we talked about at the beginning on such complex. And one final point for today is that we talked about there being an image X and one kernel or filter that gets convolved with it, and the result of it being a feature map or activation map. In these just past few slides, we've talked about a series of kernels, each of which do different types of transformations for us, such that in subsequent layers, we might combine them in even more clever ways. The series of kernels are known as a filter bank or a kernel bank. So in tomorrow's lecture, we'll continue from here and talk about both the dimensions of the outputs when we convolve large images with filter banks, and then also follow up with a bit of history of how CNNs are trained and all of the contributions that have been made by several teams of scientists over many years to get what we have today for object recognition.